In this last unit of COMP526, I want to talk about the range minimum problem. A very fundamental data structures problem that both has beautiful solutions, and it also is the missing piece that we left open in Unit 6 about the text indexing application of longest common extensions. And so this is a very nice way to wrap up this class. It will be a little bit more advanced material, so get well caffeinated definitely for the next session. We'll start slowly, and I'll warn you when I expect that you will find some of the material tough to digest at the first encounter. So let's get going with this one. What is this about? I'll start with a little bit of an introduction. What is this problem? What's this weird name coming? Where's this weird name coming from? My favorite subsection title, I won't read it out or tell you what the abbreviations mean by right now. And then we'll look at solutions for this range minimum problem. First, the simple ones that are fairly easy to understand and come up with. And then in the last two sections, we'll go to the state-of-the-art solution that's also, well, it's best possible for obvious reasons, because it's basically the time you need to read the input. And well, we'll see what's behind this last subsection then next time. All right, what is the range minimum problem? The range minimum problem, or RMQ problem for range minimum queries, is the following simple problem on an array. You're given an array of numbers. Well, it can be any comparable items. So anything you can order is actually fine. We'll use numbers in the example because these are nice and simple, but it could be strings, it could be whatever object you define an ordering relation on. The array is static, so that means it doesn't change. And the goal is to find the minimum in a range. It's a very, very simple question. Here's a range in an array, and you can find the minimum. Well, you just walk through it, and you find 2 is actually smaller than all the others, or at least there's no smaller one, no strictly smaller one. This is trivial to do if you have the time to walk through the array. The scenario that I'm interested in is we are given this array, then we can work on the array in advance, and we know the array doesn't change, so we can pre-process the array. But then we want the queries to be very, very fast. We don't want them to take linear time to scan through the array. We actually want them at the very end. Okay, I don't take that away right now. 2 little details of the definition is we report the index instead of the value. That's a minor thing because you can always look in the array. So if I say RMQ of 7 and 15 is 10, what that means is the range that stretches from 7 to 15, both inclusive, has a minimum at position 10. Okay, I don't report the 2, I report the index. That's just convenient. If you have arbitrary objects, then an index is always quick and fast to return, so you don't have to mess around with any objects. The second thing is we might have ties, like in this example. There's 2 2s. That's the only ones. And the minimum is always take the leftmost occurrence of the smallest element in the range. Okay. So far so good. I think it's a fairly simple definition, fairly simple problem. You might wonder why people care about it, because it seems so simple that there's not much you can do with it. But not so fast. It's actually very nice. Okay. To see if you're following this, let's do a very quick exercise on this. Where do you have this? Here's the question again. Just remember the 2 nitpicks. We return the leftmost index of a minimum, not anything else. Here's the array again in a little bigger. So this is supposed to be a very simple question. I'm just testing you if you're still awake, basically. And also, of course, we will build on this definition. So it's important that you have this in mind in the right way. Yeah, I'll give you a second, and well, we're not particularly in a rush, so it'd be great if we get the same 17 answers that we had before the break. Well, it seems that a few people left, so maybe 17 will be asking for too much. I guess the announcement when I said this is not on the exam, is that when when the number of viewers dropped? I'll see a few more. Maybe we can get at least 10 for this question. It's really simple. Don't overthink it. And if you don't, if I was unclear with the definition, say I don't know or didn't understand the problem, that's also fine. I'm happy to repeat that before we move on. Okay, we have 7. Maybe we can get our 10 answers before I show you what you voted. Two more, guys. I know it's getting late in the term. Yep, 9. Okay, I see there's creative answers in there. One more. Great. There we go. And there seems to be a preference for 1. Let's see if that is what we expect. So what does that mean? Okay, range minimum query. So first of all, we have to find the range that this is talking about. That's 1 up to 7. That's not too hard. We'd go from 1 up to 7, and it's inclusive. So that's the range we talk about. We're only looking at this range of the array. So if you wanted, and if that worked well, you could zoom in and say we're only looking at this tiny portion of the array. And now we're looking for the minimum in this range. Well, 4 seems to be the smallest number. It occurs twice. But remember the second nitpick, we always report the first occurrence. So this is where our minimum is. And then the last nitpick, we don't report 4, we report the position. So that's this 1. So 1 is the answer. Good, well done. Let's zoom this again. Okay, good. So everyone's up to speed now, I hope. We find the minimum in the range. We find the leftmost occurrence of that minimum. We return its position. That's RMQ, range min query. All right. Good. So we know what the problem is now. A little bit of commentary around this. We ask for the minimum, so all we really ask for is a comparison-based question. We can do this for arbitrary objects, so the values don't really matter. The only thing that matters is the relative order they appear in the array. In other words, if you give me one array and another array, and the only thing they differ in is the types of objects or the values, but the relative ranking is the same, then every arrangement query will have the same answer. Simple consequence of returning the index and not the value. Now, unlike other algorithms that we talked about, we have more quantities of interest in terms of running time here. We're already used to have time and space. Now we have 2 different times as well. We have the pre-processing time, where that's how much time we take initially to look at the array A and do something smart with it. And we have the query time. That's the time it takes to answer the arrangement queries using the data structure we built in the pre-processing step. A nice result here also, just because, okay, first state what it says. If the pre-processing time is at most P of n, that also means the space usage of the data structure is at most P of n. Simply because suppose the data structure would be bigger, you would at least need the time in the pre-processing step to write down the data structure. So there's no way you can create something bigger than you have time to write it down. You need to write it down, and that takes time. So by bounding the pre-processing time, we automatically bound the space of the data structure. So when I say here 2 main quantities of interest, that's a bit of a lie. We do care a lot about the space. It's just that by bounding the pre-processing time, we automatically get a bound on the space, and that will be in general already enough to have a best possible solution. So a little piece of notation here is this angle brackets. Because we have 2 times, we want to make clear which one is which. So I'll always give the pre-processing first and then the query time, because pre-processing comes before query. That makes sense, I hope. And so we'll just write this as a shorthand notation. Okay. So that's the idea. You're given this array. You can look at it, take your time. You pay for that in the P of n entry. And then once you're done, I'll fire you. I'll fire so many arrangement queries at you potentially. And then how long you take for each, that's the Q of n. So now I want to see just some wild random guesses. What do you think, without knowing the problem, without having really thought about it, without really haven't been given the time to think about it, what do you think? What combination of P and Q is possible to attain? And yeah, I set this up so that you can send multiple answers. So maybe there's different combinations between P and Q. There's a trade-off between pre-processing and query time. That's maybe natural, because there's also a trade-off between time and space. If you write down many more things, maybe the queries get easy. And if you write down nothing, then the queries can't be very fast. So what I'd like to see is this pair of functions, and it really should be 2 theta classes, I think. I didn't write this here, but it would probably make sense to send 2 theta classes, one for pre-processing, one for query. Okay, I meant just something. For example, you could write angle brackets of theta square root n comma theta n to the 5 or so. Obviously, these don't make sense. I don't want to give you any anchor so that you're free to come up with the answers any way you like it. And I think you can see the answers anyway, so I might as well show this. Okay, you might want to edit the P of n. Yeah, so the 2.5, I mean, this doesn't work for arbitrarily large inputs. We have order n for a couple of things. What's that, pre-processing or query or both? Theta and theta n, that's interesting. Theta n order 1, I should probably highlight this here. That's definitely the best you can possibly get, because you need at least linear time to read the array in the pre-processing step if you want to do anything intelligent. And you need at least constant time to report the answer to arrangement query. So if you could get this theta n theta 1, then we'd be very happy. This one, theta and theta n, is definitely doable, because basically In linear time, we can easily solve the arrangement queries even without pre-processing. I'll come back to that in a second.